Hello, this is a revision video for AP Chemistry, Chapter 6. As this is a revision video, only the essential information is covered. For more detailed explanations and full video lessons, please check the links in the description below. Good luck revising.
Temperature is directly related to the average kinetic energy of particles in a substance. As temperature increases, the particles move faster because their kinetic energy increases. All chemical reactions involve energy changes. To understand and model how energy is transferred in a chemical reaction, we define two parts: the system and its surroundings. The system is the reacting substances, so the chemical species that actually change in the reaction or process. And the surroundings are everything else. So they may be water molecules in a solution, gaseous air particles for an open reaction, or even the walls of the container. The energy change of a reaction is the result of energy exchanged between the system and its surroundings. By observing the temperature change of the surroundings, we can determine the direction of energy flow. If energy is released from the system to its surroundings, we say it is an exothermic reaction or process. Products are lower in energy than reactants, and the difference in energy is released as heat. This means the surroundings become warmer, temperature increases, and the overall energy of the system decreases, a negative energy change. Common examples include combustion and neutralization. If energy is absorbed by the system from its surroundings, we say it is an endothermic reaction or process. The products are higher in energy than the reactants, and the difference in energy is absorbed as heat from the surroundings. As a result, the surroundings become cooler, temperature decreases, and the overall energy change of the system is positive. A common example would be thermal decomposition, such as the thermal decomposition of calcium carbonate. The key idea here is that the temperature change of surroundings is the key observable sign of energy transfer. If the surroundings increase in temperature, the reaction or process occurring must be exothermic. And if the surroundings decrease in temperature, the reaction or process must be endothermic. Enthalpy change refers to heat energy change per mole measured at constant pressure, but this is covered in much more detail later in the course under AP 6.6, Introduction to Enthalpy of Reaction. In both chemical and physical changes, we can model energy transfer by heat, Q, and work, W, where heat is the transfer of thermal energy due to temperature difference, and work is the energy transfer from volume or pressure changes. As a result, the total energy change that occurs for a reaction or process is given by change in energy equals Q plus W. An interesting case to look at in chemistry is the dissolving of a solute in a solvent, as this can sometimes be endothermic or exothermic. When a solute dissolves in a solvent, energy is required to overcome the attractions holding solute particles together in the original solute, and energy is also required to overcome interactions between solvent molecules in the solvent. However, energy is also released as new solute-solvent interactions are formed in the resulting solution. Now, if forming new interactions between solute and solvent particles releases more energy than is needed to break apart the interactions between solute and solvent particles, the overall process is exothermic, a negative energy change. However, if overcoming the interactions in the solute and solvent originally requires more energy than is released when new solute-solvent particle interactions form, then now the process would be endothermic with a positive energy change. An energy diagram is a graphical way of showing the overall energy change that occurs during a chemical reaction or physical process, so starting and final energy levels. The y-axis represents potential energy. For an exothermic energy level diagram, the products will be at a lower energy than the reactants, and the difference between them is the overall energy change of the reaction or process. This difference in energy being released to the surroundings as heat. For an endothermic energy level diagram, the products will be shown at a higher energy level than the reactants. And again, the difference between them is the energy change during the reaction, with this energy coming from the surroundings. Energy diagrams also apply to phase changes and other physical processes and transformations. For example, ice melting and water freezing can be shown on an energy diagram. Technically speaking, energy level diagrams and reaction profile diagrams can mean slightly different things in the world of chemistry. However, for the AP Chemistry course, the two terms are used interchangeably, so don't worry if you look on the internet or at other resources and see some confusion regarding the terms energy level diagrams and reaction profile diagrams. For AP Chemistry, they basically mean the same thing. Temperature is a measure of the average kinetic energy of the particles in a substance. In a warmer object, particles move faster, and in a cooler object, particles move slower. When two objects at different temperatures come into contact, energy is transferred through collisions between particles. When a fast-moving particle from a warmer object collides with a slower particle from a cooler object, some energy is transferred. The warmer particle slows down and the cooler particle speeds up. This process continues with more collisions. The combined total energy of all particles is conserved but redistributed between them. This flow of energy is called heat transfer, also known as thermal energy transfer or energy exchange. Exam tip here: heat transfer always occurs spontaneously from higher to lower temperature. Energy doesn't flow from cold to hot unless work is done, for example in refrigeration. Over time, as energy is exchanged between two objects or systems, the temperature difference between them decreases. Thermal equilibrium is reached when both substances have the same average kinetic energy and therefore the same temperature. At this point, there is no net transfer of energy between the systems. However, you should be aware that technically particles from both systems are still colliding and exchanging energy, it's just there is no net transfer of energy between them. When a substance is heated or cooled, its temperature changes. This temperature change is proportional to the heat added or removed, the amount of substance change in temperature, and the substance's ability to absorb energy. This is summarized in the equation for heat transfer, Q equals mcΔT, where Q is the heat absorbed or released, m is the mass of the substance in grams, C is the specific heat capacity of the substance, and delta T is the temperature change of the substance, so final temperature minus initial temperature. Specific heat capacity just refers to the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. Its usual units are joules per gram per degree Celsius. A larger specific heat capacity means the substance resists temperature change, and it therefore needs more energy to heat up by a certain amount. For example, water has a much higher specific heat capacity than copper. This means that for equal masses, copper will heat up more quickly than water when the same amount of energy is applied. The specific heat capacity of water is 4.18 joules per gram per degree Celsius, whereas for copper it's only 0.39 joules per gram per degree Celsius. So to heat 1 gram of copper by 1 degree Celsius, you only need 0.39 joules of energy. Whereas to heat 1 gram of water by 1 degree Celsius, you need 4.18 joules of energy. Calorimetry is the experimental technique used to measure heat transfer. During an experiment, the temperature change of the reaction's surroundings is measured. If you're unsure about this, please check AP 6.1, endothermic and exothermic processes. But as a quick recap, if temperature increases, the process is exothermic, the reacting system is releasing heat. Whereas if the temperature decreases, the reaction process is endothermic, it absorbs heat. Exam tip here: for calculations involving calorimetry, assume no heat is lost to wider surroundings unless told otherwise. For example, if a combustion is taking place and water is being heated, assume all the energy being released from the combustion process is transferred to the water being heated. This isn't strictly speaking true, because some energy will also be lost to the wider surroundings, such as gaseous air particles around the combustion reaction. However, unless you're told otherwise, we always assume for Q equals mcΔT that no heat is being lost other than to the surroundings being studied. The first law of thermodynamics states that energy is conserved. This means energy cannot be created or destroyed. It can only be transferred or transformed. Heat lost by one substance must be gained by another. You need to be aware of the difference between specific heat capacity and molar heat capacity. We've already seen specific heat capacity is the energy needed to raise 1 gram of a substance by 1 degree Celsius. whereas molar heat capacity is the energy needed to raise 1 mole of a substance by 1 degree Celsius. Be careful to make sure you're matching units to the type of heat capacity you're using for a given question. In calorimetry experiments involving dissolution, so the dissolving of a solute in a solvent, if the temperature of the solution increases, the process is exothermic. If the temperature of the solution decreases, the process is endothermic. Here we are modeling the surroundings of the process as the solution itself. When a substance changes phase, it absorbs or releases energy. Importantly, it is the breaking or forming of forces holding a substance together that determines this energy change. Melting and boiling are endothermic, energy is absorbed, and freezing and condensation are exothermic, energy is released. However, during all of these processes, the temperature of the substance doesn't actually change. This can be seen on heating curves. For example, if we plot temperature over time while heating solid ice, we can see 2 flat lines or plateaus where the temperature doesn't change. These represent the phase changes of melting and boiling. During these stages, energy being applied to the system is being used to overcome forces of attraction between water molecules in the system. This means the energy being applied isn't used to increase the temperature. The temperature can only start increasing again when the phase change is complete, so when all of the solid has melted, or when all of the liquid has turned into gas. Then, if you keep increasing energy, the added energy makes the particles move faster and therefore causes an increase in temperature. We can use the number of moles and the appropriate molar enthalpy values to calculate heat transfer during phase changes, where Q equals N times enthalpy change of fusion, and Q equals N times delta H vaporization for boiling or condensation, where Q is the heat absorbed or released, N is the amount of moles of substance undergoing the phase change, delta H fusion is the molar enthalpy of fusion, so melting and freezing, and delta H vaporization is the molar enthalpy of vaporization, so boiling or condensing. Now for melting, delta H fusion will be positive, and for freezing, delta H fusion will be negative. And for boiling, delta H vaporization will be positive, and for condensing, delta H vaporization will be negative. This is because energy changes are equal and opposite for complementary processes. So the amount of energy required to melt 1 mole of a substance will be the same amount of energy released when 1 mole of the substance refreezes. The enthalpy change of a reaction, delta H, describes the amount of heat released or absorbed during a chemical reaction at constant pressure, and has units of kilojoules per mole. For exothermic reactions, delta H is negative, heat is released, and for endothermic reactions, delta H is positive, heat is absorbed. In a chemical reaction, bonds are broken in reactants and new bonds are formed in products. These changes affect the chemical potential energy of the system, and the energy difference results in a change in kinetic energy of the particles, which causes a temperature change. This is outlined in more detail in 6.7. Bond enthalpies. If you know the heat energy change Q for a reaction or process, you can determine the enthalpy change per mole using delta H equals negative Q divided by N, where delta H is the enthalpy change per mole, Q is the heat energy change of surroundings, and N is the number of moles of limiting reagent. The negative sign included in the equation accounts for the fact that Q measures the heat gained or lost by the surroundings, whereas delta H refers to the energy change of the system. Now, if Q is positive, so the surroundings gain heat, the system has released energy, so delta H must be negative. And equally, if Q is negative, so the surroundings have lost heat, the system must have gained energy, so delta H is positive. You can also rearrange this formula to calculate Q if delta H and N are known, where Q equals N times negative delta H. This form is useful when enthalpy change is provided in a reaction equation and you want to find the total heat energy change that would go into the surroundings. Exam tip here, always make sure that the moles you use in your delta H equation are the moles of limiting reactant for a given reaction or process, and ensure all units are consistent. This is particularly relevant for Q, as Q is usually given as joules, but enthalpy change is given in kilojoules per mole, so to convert joules to kilojoules, divide by 1000. In an exothermic reaction, the system loses energy and heat flows to the surroundings, so the temperature of the surroundings goes up. In an endothermic reaction, the system gains energy. Heat flows from the surroundings to the system, so the temperature of the surroundings goes down. These thermal energy changes are observed as a temperature change in calorimetry experiments, assuming the reaction happens at constant pressure. Bond enthalpy is defined as the energy required to break 1 mole of a particular bond in the gaseous state. This is also sometimes referred to as bond dissociation energy. Breaking bonds requires energy. It's an endothermic process, whereas making bonds releases energy. It's an exothermic process. This is because to break a covalent bond, energy is required to overcome the attraction between the shared pair of electrons and the positively charged nuclei of each atom. As a result, the potential energy of the atoms goes up when the bond gets broken. Equally, when these atoms with a higher potential energy then form covalent bonds again, their potential energy will decrease and they will release energy, making the process exothermic. Mean bond enthalpy is the average energy required to break a particular bond type, averaged over several molecules containing that bond. For example, the mean bond enthalpy of a carbon-hydrogen bond is positive 412 kilojoules per mole, but the exact amount of energy required to break a carbon-hydrogen bond will be different in different molecules because their environment is slightly different. Now, these differences are very small, however, you should be aware that because mean bond enthalpies are averages, enthalpy calculations using them are approximate compared to experimental values that we get from calorimetry experiments. The enthalpy change of a reaction can be estimated using enthalpy change equals sum of all bond enthalpies in reactants minus the sum of all bond enthalpies in products. Exam tip here, remember experimental values from calorimetry are usually more accurate than those calculated using bond enthalpies. The standard enthalpy change of formation is the energy change when 1 mole of a compound forms from its constituent elements in their standard states at 298 Kelvin and 1 atmosphere. As a result, by definition, elements in their standard states have an enthalpy of formation of 0. We can calculate the enthalpy change of a reaction by using the standard enthalpies of formation of the reactants and products. We use the formula delta H of reaction equals sum of all enthalpies of formation of products minus sum of all enthalpies of formation of reactants. Now, it's really important to point out that we have to multiply each substance's enthalpy of formation by its coefficient, so molar ratio, in the balanced equation. For example, to calculate the enthalpy change for the reaction CH4 plus 2O2 to CO2 plus 2H2O, we can use the standard enthalpies of formation of the CH4, O2, CO2, and H2O to do it. Well, the total standard enthalpy of formation of the products would be 1 times minus 393.5 for the 1 mole of carbon dioxide, 2 times minus 285.8 for the 2 moles of H2O, giving us minus 965.1 kilojoules. And the sum of enthalpy of formation of the reactants would be 1 times minus 74.8 for the 1 mole of CH4 and 2 times 0 for the 2 moles of O2. Notice that O2 has an enthalpy of formation of 0 because it's an element in its standard state. Therefore, the enthalpy change of reaction would be minus 965.1 subtract minus 74.8, given minus 890.3 kilojoules per mole. Exam tip here. Always base your calculations on a balanced chemical equation and account for the molar ratios, so the coefficients, of all substances involved. For example, if the balanced equation shows 2 moles of something are formed, you must multiply the enthalpy of formation for that substance by 2 when calculating the total enthalpy change. This is a common area of lost marks for students. Many chemical and physical processes occur in multiple steps, with each step having its own enthalpy change. Hess's law states the total enthalpy change for a reaction is the same, regardless of the pathway taken, provided the initial and final conditions are the same. This means we can calculate the overall enthalpy change of a reaction by adding the enthalpy changes of individual steps together. Hess's law is a consequence of the first law of thermodynamics: energy cannot be created or destroyed. The total energy change only depends on the initial and final states, not how the reaction gets there. It's a bit like climbing up a mountain. It doesn't matter which route you take to go up to the top of a mountain, your overall change in altitude will be the same regardless of the route you've taken. Whether a process happens in one step or several, the total enthalpy change will be the same if the start and end points are the same. Exam tip here: Hess's law only applies when the starting and ending conditions, like temperature and pressure, are the same in each pathway. Always double check this before applying the law, and don't get caught out. Hess's law is useful when it's difficult to directly measure the enthalpy change of a reaction. Instead, we can use enthalpy cycles and other measured values to calculate it indirectly. There are a few key rules you should be aware of for Hess's law. When reversing the direction of a reaction, we reverse the sign of delta H. For example, if a reaction is endothermic in one direction, it must be exothermic in the reverse direction. So if A going to form B is endothermic, then B reforming A must be exothermic. When multiplying a reaction, we multiply delta H by the same factor. For example, if A going to form B has an enthalpy change of 50 kilojoules per mole, then 2A going to form 2B will have an enthalpy change of positive 100 kilojoules per mole. Because it's twice the quantity of A reacting, it will be twice the enthalpy change. When adding reactions together, we add the enthalpy change for each reaction. So the overall enthalpy change is the sum of each individual step. For example, if A going to form B has an enthalpy change of positive 50 kilojoules per mole, and B going to form C has an enthalpy change of minus 20 kilojoules per mole, then overall, if A reacts to form C, the enthalpy change will be positive 30 kilojoules per mole. We're adding the two enthalpy changes together, so positive 50 plus minus 20, to give positive 30 overall.